4 builds on power functions, and in this module we will discuss linear functions, polynomial functions, and rational functions. We will talk about the general forms, the domain and range, the graphs, the intercepts, and some of the common techniques to approach these functions with. We will start with linear functions or lines. Recall that a linear equation in two variables, x and y, generally, is an equation that can be written as ax plus by equals c, where a, b, and c are some kinds of real constants where both a and b cannot be 0. So you cannot have an equation like 0 equals to c. A linear function, therefore, is a function of the form mx plus b, where m and b are two real numbers. Notice that what makes an equation or a function linear is the fact that in both the instances, whatever variables you have, x and y in this case, or visibly just x here because y is represented by the function of x, are both to the power of 1. So all the powers of variables that appear are 1. Now the functions are called linear because their graph is of course a line, and this should not be a big surprise to anyone. There are a number of different ways that one can write equations of lines in. Now note that an equation of a line is unique in a sense that a single equation describes a uniquely determined line, but the equation can be rewritten in different shapes and forms depending on what is more convenient for you. So a standard form is the one that we actually see up here. It is the form ax plus by equals 2c. The slope-intercept form is the one that appears in the definition of a linear function. So y, or f of x, equals mx plus b. Now the reason it's called slope-intercept form is because the m is the slope and the b is the y-intercept. So let's label them as such. This is slope, this is the y-intercept. Of course, it becomes fairly clear why this is called the y-intercept. Recall that a y-intercept is where the graph intersects the y-axis, which means that that point x is 0. So if I plug in x equals 0 into this equation, this entire term will turn to 0, leaving me with y equals b, which is what makes it the y-intercept. Point-slope form of the equation of a line is one of the most useful line forms in calculus, and it is written in this way. Y minus y naught equals m times x minus x naught. So here, once again, m represents the slope, but this y naught and x naught represent coordinates of one point on the line. You can pick any point on the line to go into this equation. If you move things around in this equation, you will also see that it's actually saying nothing other than the fact that the slope, so if I divide both sides by x minus x naught, it will appear on the left here, and then the equation will turn into the slope being equal to rise over run, which is a very familiar statement. In fact, slope is what we're going to talk about next. Slope is one of the defining properties of a line, and we generally given a line compute it as rise over run. So slope is a measure of steepness of a line. The higher the number, the steeper the line is. It's also constant along the entire line. So it does not matter which 2 points on the line I compute the slope at. Any 2 points on the line will give me the same slope. The slope along any line is a constant number. So whether I compute it between these 2 points or I compute it between some other 2 points, let's say these two or these two, the rise and the run will change, but the ratio between them, which we call slope, will not. The slope will be positive for lines that are increasing or what they look like they are pointing uphill. So this line will have a positive slope, and the slope will be negative for the lines that are decreasing. this will produce a negative slope. So if you're walking along the line from negative x to x, if you are going down the hill, that indicates negative slope. If you're walking up the hill, that indicates positive slope. Apart from slanted lines like we see here, there are of course vertical and horizontal lines, and they will have equations that are slightly different from the forms that we've seen before. So let's think about those for a second. If I quickly sketch what a vertical and a horizontal line would look like, it will give us some clue as to what an equation can be. So for example, let's think about a vertical line first. Here's a vertical line. Let's say I assign a specific point, like 5 here. What is true about the coordinates of the points on this line is the fact that no matter what point on the line I pick, the x-coordinate will always be 5, while the y-coordinates will range from negative infinity to infinity. But the x-coordinate stays the same, which motivates the fact that vertical lines have equations x equals some constant. Thinking about the slope of this line, if I take rise over run between any 2 points, my rise will be some number because I have risen some amount, but the run will be 0. I cannot divide by 0, which means that for vertical lines, the slope is undefined. For horizontal lines, we have a situation that is similar, but of course now instead of vertical, horizontal. So let's say I have a horizontal line up here. Let's say it's somewhere at like 7, just for the sake of picking some numbers. Thinking about the points on this line, I notice that the y-coordinate of them all is 7, whereas the x-coordinate ranges from negative infinity to infinity, which means that horizontal lines will have equations of the form y equals a constant. Thinking about the slope here, if I pick 2 points on a horizontal line, I have risen none or 0, and I have ran some amount, so some number k, let's say. I can divide 0 by k, and I will simply get a 0. So the slope of the horizontal line is equal to 0. So we think about the horizontal lines as completely flat, no steepness to them at all, whereas vertical lines are as steep as one can be, infinitely steep. There are a number of ways that the lines can interact with each other. For example, lines can be parallel, which will mean, of course, that we have a picture that looks something like this. Parallel lines do not intersect, but what makes them parallel is that they have the same steepness or the same slope. So what characterizes parallel lines is the fact that they have equal slopes. Perpendicular lines are the lines that meet at the angle of 90 degrees, at the right angle. So for example, these two lines that I have sketched here look like they're approximately perpendicular. What is true about the slopes of these lines is, as we've seen here, if one of them is positive, the other one has to be negative. And in fact, something even stronger is true. The rise over run switch completely. So the slopes of perpendicular lines are negative reciprocals of each other. If we think in terms of domain and range, we have to separate vertical and horizontal lines from all the other sloped lines. If I have a sloped line, then I can see that the domain and the range will be all real numbers, as this line will continue along all of the possible x's and along all of the possible y's. Whereas if I have a vertical or a horizontal line, then I will have constraints on my x and y values. So here, for sloped, I'm going to call them sloped lines. Both domain and range are all real numbers. But for vertical and horizontal lines, the situation is quite different, and I'm going to give you an opportunity to come up with the expressions for the domain and range yourself here. Now, in terms of graphing, there are a number of ways to graph lines, and we're just going to discuss a couple of them and see a few examples in a minute. Now, the first thing you can do, as with any other graph, is to simply plot some points. Now, in the case of lines, what is nice is that 2 points is actually enough to uniquely determine a line. So you really only have to plug in 2 points. you're going to plug in 2 points. There are 2 particularly nice points that one can use, and they are the intercepts. Right? So just plug in y equals 0 and x equals 0. You're going to get your 2 points on 2 axes and a unique line through them. And then, of course, you can somehow utilize the slope, whether you use it directly from the slope-intercept form or from any given point. It is one of the other ways to sketch a line. There are, of course, a number of other techniques. Let's take a look at a couple of examples where we'll see how to use that, as well as how to generally come up with equations of lines, given different information about them. So the first example asks us to sketch a line and find an equation of it through a particular point with a specified slope. So let's start by producing a little sketch here just to see if we understand what this line looks like. So it goes through the point 1, 1. Here's a point 1, 1. And it has a slope of 3. So remember that the slope is rise over run, which means that it's actually better to rewrite 3 as 3 over 1, as it makes rise and run clearer. This is why, while the ratio is unique, the rise over run or the choice of points doesn't have to be, because I could have rewritten 3 as 6 over 2, and then my rise would have been 6 and my run would have been 2. I chose to do the smallest version of 3, but you can pick any form at all. So that means that from the point on the line that I have to rise 3 and run 1 to get another point on the line. Okay, so let me note that. 1, 2, 3, and I have to rise 1. This is going to be my next point on the line. Okay, as I've just mentioned, 2 points determine a line uniquely, so I'm going to have a line through them that I can already draw. Notice that instead of, as I was saying, 3 over 1, I could have used 6 over 2, which means I would have had to rise 6 from this point and run 2, and I would have gotten the next point on this line if I extended. I also could have dropped 3 and unran 1, which, starting from this point, for example, drop 3 and unrun 1, my scale here is a little bit off, I would have gotten a point on the line that belongs to there. Okay? Now, in terms of finding the equation of this line, you can use any of the forms of the line that we've discussed on the previous slide. The standard form, a slope-intercept form, or the point-slope form. Depending on the information that you're given, one of them will probably produce the fastest result. Here, we are given a point and a slope, which means that the point-slope form will probably be the most efficient method to come up with an equation of this line. So here is the general form of that equation. And let's fill in the information that we know. So we know that our slope is 3, and we know that there is a point on our line with coordinates 1, 1. So my x-coordinate of a point is 1, and my y-coordinate of the point is 1. Filling all of that in, I will have y minus 1 equals 3x minus 1. And this is the equation of my line. If you prefer the equations of your line in a slope-intercept form as the final answer, or your online homework system demands it, or you're going to have to use it for something else, we can turn this form into any other form that we want. So I'm going to simply open up the brackets on the right, so 3x minus 3, and then I'm going to move this 1 over to the right and subtract it from 3, and overall I'm going to get 3x minus 3 plus 1, so minus 2. So this is the exact same line, but now in the slope-intercept form. So I notice that the slope here is 3, and the y-intercept is negative 2, which will be this point right here. Again, my scale is a little bit off on the sketch, but that's okay. Let's take a look at the next example. Find a sketch equation of a line through points 1, 1 and 2, 5. So as opposed to the previous example, I am not given the slope, I am given 2 points. So again, before we actually look for the equation of a line, let's sketch a little picture. So my points are 1, 1 and 2, 5. So this point right here, and I can sketch a line through them. Once I have 2 points, the line is unique. Great. So what I do need, first of all, is to come up with the value for the slope. Okay, so what do we have in this case? Slope is rise over run, And it doesn't matter which way you go from the first point to the second or from the second to the first. The rise is the difference in y's, so 5 minus 1, and the run is the difference in x's, so 2 minus 1. So I get 4 over 1, or 4, and we can see that this is exactly what happened here. I have risen 4 and ran 1. Okay, so now I have a value for the slope, and I have two different points. So once again, the point slope form of the line is probably the most useful one, so I'm going to go with that one again. And in fact, this is the form that you will likely use the most in calculus anyways. So notice that my slope is, of course, 4, as we've just computed, but I have a choice of which point to plug in as my point into the equation. Either one of them will work, and in fact, both of them should give you the exact same result if you simplify the equation to the point slope, or to the slope-intercept form. So I can have y minus y equals 4x minus 1, or I can have y minus 5, if I use the second point, equals 4x minus 2. Okay, either one of these will be correct. And again, notice that if you open up the brackets and move things around, both of them will give you the exact same equation of a line, which is y equals 4x. Let's just trace that out. 4x minus 4 plus 1 would have given you minus 3. And this will be the result coming out from either one of these equations. Okay? Good. Let's take a look at this next example of sketching and finding equation of a line. We're now given a point, and we're told that our line has to be parallel to this other given line. So let's first of all sketch a picture just to get a sense of what information we're given and what information we're trying to get. So I have my line that I don't know the equation of that has to go through the point 3, 1. Okay, so it has to go through the point 3, 1 right here. What I do know is, I don't know of its slope, but I do know that it's parallel to this other line, 2x plus 3y. Okay, how am I going to sketch this line that I know my line is parallel to? Well, there's a number of ways. This is in the standard form, which means that the slope is not easy to read straight off of the expression. So one thing I can do is simplify this to be in the slope-intercept form, and then be able to read the slope and the y-intercept, or I can plug in the points. In this case, plugging in the x and y-intercept is actually fairly easy. So for the y-intercept, I set x to be 0. And what am I going to get when x is 0? Well, you know what? Let's just change this to 6 to simplify our arithmetic a little bit. So if x is 0, this whole term will go away, and then I have the equation 3y equals 6, which means that y will be equal to 2. If I set y to be 0, so if that's for the other intercept, then this entire term will go away, and I will have the equation 2x equals 6, which of course then means that x has to equal to 3. So these are my two intercepts, and intercepts are usually very easy to get from a standard equation of a line, and I can sketch those 2 points. Okay, so this line has the, when y is 0, x is 3, so this point right here, 3, 0, and when x is 0, y is 2, so this guy right here, 0, 2. Okay, so this line that my line has to be parallel to has to go through these 2 points. So my line will then have to look something like this. Now, we know that parallel means that the slopes are equal. Let's write that down, equal slopes. The problem is, the slope of this line, I cannot read straight from the equation. Now that I've sketched it, and I already have some points on this line, there are once again a number of ways to actually compute the slope of this line. I do have 2 points, so we can compute slope as rise over run between those 2 points, which will be, so the rise is the difference in y's, 2 minus 0, divided by the run, which is the difference in x's, which will be 0 minus 3. So in total, I'm going to get minus 2/3. The other way to get the slope, or to have sketched this line to begin with, is once again to put this equation into the slope-intercept form. So let me just show you the second method here as well, and you can choose whichever one you prefer to follow. So in order to put this equation into the slope-intercept form, I have to solve it for y. So I'm going to have to isolate y. So my first step will be 3y equals minus 2x plus 6. And then I'm going to solve for y, which means I have to divide everything by 3. So minus 2/3 x plus 2. Okay, so this is now the slope-intercept form of this equation. And I can easily see that my slope here is the coefficient in front of x, which is minus 2/3. Okay, so the slope, same as here, is 2/3. So both of my calculations resulted in the same slope, which is great news. Okay, now this is the line's slope that is parallel to my line. What about my line itself? Once again, it's easiest in this case to go through the point slope equation of a line. My line has to have the same slope as the line it's parallel to, which means that the slope will be minus 2/3. And I also know a point on my line that was given to me to begin with, and that was 3, 1. So x is 3, y is 1. So altogether, the equation of my line comes out to be y minus 1 equals minus 2/3 x minus 3. All right, and once again, this equation is perfectly good equation of a line, but if you prefer your equations in the slope-intercept form, or you need it to be in the slope-intercept form, you can then simplify this to be in that form by opening up the brackets and moving the coefficient, the constant over to the right-hand side. Let's take a look at a problem that involves sketching lines. So I have a car that leaves town at 60 kilometers per hour. I am wondering how long will it take a second car, which is traveling faster at 90 kilometers per hour, to catch the first car if the second car leaves an hour later. So what we know is the time frame for the second car leaving, and we also know the speeds of both cars. So let's take a look at, maybe let's sketch a graph, keeping that in mind. Now on the graph though, we're going to have to decide what it is that we are actually sketching. Okay, I have time and I know something about speeds, right? So it probably makes sense that the time is my independent variable. I can choose how far into the journey I'm computing something about these cars in, but what should be my vertical axis here? Should it be speed or should it be distance? And the key here is to think about the units. 60 kilometers per hour. This is already my x-axis, and this in kilometers, if I make my vertical axis distance, then this will be then a relationship of rise over run, and therefore a slope, which is something that I should be able to graph fairly easily. So let's make our vertical line, a vertical axis, distance. Okay, so then what can I say about the first car? Well, the first car left at time 0, and it's traveling at 60 kilometers per hour. So in 1 hour, it's going to be 60 kilometers away. In 2 hours, it's going to be 120 kilometers away, and so on. So I can draw this line, and the equation of this line is fairly easy to see. I can see that the slope is 60. And I can see that the y-intercept is the origin, because I set my time to be 0 when the first car left. So it's going to be 60x plus 0, or simply 60x. For the equation of the line that corresponds to my first car. Let's think about the second car. The second car left an hour later. So in time here, the first car left at 0, the second car left an hour later, which means it left at 1 in terms of time. And it's traveling at 90 kilometers per hour, which means that in 1 hour, so at the 2-point mark for the first car, the second car is going to be at 90 kilometers, which is halfway here. So in 2 hours, it's going to be here. In 3 hours, it's going to be 90 plus 90, or 180. Now I know 180 is divisible by 60, so I actually have a suspicion that these two lines will cross here. But okay, let's come up with the equation of this line that corresponds to the second car. So I know that it's traveling at 90 kilometers per hour, which means that this is going to be the slope of my second car. And I also know a couple of points on the line. In particular, for example, I know where it starts off at. So once again here, I can use my point slope form to come up with the equation of this line. So my slope is 90. And the point that I have is when time, or x, was 1, it had just started off, so the distance was 0. So overall, my equation is going to be y minus 0 equals 90 times x minus 1. Okay, so this is the equation of my second car's travel. Excellent. Now I have two equations of two lines, and the question really is, how long will it take the second car to catch the first car? So I really am wondering, when are they going to meet? They're going to meet at a point where the x and the y coordinates are equal. So I can simply set their equations to be equal and then solve for x. Okay, so setting equations to be equal. What are we going to get? My first equation was y equals 60x. So 60x has to be equal to my second y value, which is 90 times x minus y. And this is a simple linear equation. I only see x's to the power of 1. So I can open up the brackets, move things around, and I will get 30x equals to 90, or x equals to 3. I've computed the value for x, which is in this case the time. If you want to compute the value for y, you can plug it into either one of these equations, because this is the point that they have in common. So either one of them works. Obviously, it's easier to plug it into this one. When x is 3, y is going to be 180. So the two cars will meet 3 hours from the time that the first car had left, at the distance 180 kilometers away from the original point that they left from. Please take a look and complete the web work assignment module 4a that includes a lot more practice on various equations of lines and various information provided about them. Also, please take a look at exercise at the end of the section, where there are not just questions on coming up with equations of lines, but also questions that involve modeling with linear functions, as well as obtaining flexibility going from a sketch to an equation of a line, or the other way around.